Hello, everyone. Today, I'll be introducing generative cooperative networks, also known as CoopNets. These models offer a powerful way to bridge the gap between two widely used generative frameworks, energy-based models and latent variable models, by training them cooperatively. Generative cooperative networks combine two key components: an energy-based model, which we call the descriptor, and a latent variable model, known as the generator. The generator proposes initial synthetic data samples, and then the descriptor refines them using Langevin dynamics. After that, the generator learns from the refined samples, effectively improving itself over time. This cooperation makes the training more stable and sample generation more efficient. To better understand how generative cooperative networks work, let's consider this analogy. Imagine a student who writes an initial draft of a paper. The advisor then revises it, and they submit the improved version for review. The student learns from the advisor's revisions, and the advisor improves based on feedback from the reviewers. The advisor guides the student, but the student does most of the work. This captures the core idea of generative cooperative networks. Now, why do we need cooperative networks? Energy-based models are very expressive, but difficult to sample from. Latent variable models are easy to sample from, but may struggle to capture complex data distributions. Cooperative networks address these limitations. The generator adopts ancestral sampling to initialize the iterative MCMC sampling for the energy-based model, and the energy-based model, in turn, guides the generator to produce better synthesized examples. It's a symbiotic training process. Before we dive into the details of cooperative learning, let's first review each component of the framework. We begin with the descriptor, which is an energy-based model. It is parameterized by a bottom-up neural network f of x, where alpha denotes the model parameters. Learning the energy-based model via maximum likelihood leads to an analysis by synthesis algorithm that alternates between a sampling step and a learning step. In the sampling step, the model draws samples using Langevin dynamics, which provides approximate samples from the model distribution. In the learning step, the parameters alpha are updated via gradient ascent, where the gradient is estimated based on the MCMC samples obtained in the sampling step. Next, let's discuss the other component of the framework, the generator, which is a latent variable model. The generator assumes that each data example can be generated by transforming latent variables drawn from a prior distribution. This transformation is modeled by a neural network G of Z, where theta are the generator parameters. Learning latent variable models via maximum likelihood involves alternating between an inference step and a learning step. In the inference step, given an observed data example, the model infers its latent variables by sampling from the posterior distribution using Langevin dynamics. In the learning step, the parameters are updated via gradient ascent, where the gradient is estimated using the inferred latent variables obtained during the inference step. Now let's talk about the cooperative learning algorithm and see how a descriptor and a generator cooperate with each other to synthesize better examples. The diagram on your left-hand side illustrates the basic idea of the cooperative learning. Each iteration of the cooperative learning algorithm consists of the following steps. First, we sample latent variables from the prior distribution, which is a known Gaussian distribution. Second, the generator generates initial synthesized examples by transforming the latent variables. Third, the energy-based model revises the initial synthesized examples using Langevin dynamics, which is guided by the energy function. Fourth, the generator infers the latent factors for the revised synthesized examples. Fifth, we update the descriptor based on the revised examples and the training data. Sixth, we update the generator based on the inferred latent variables and the revised synthesized examples. In this cooperative learning, the generator acts like a student who writes an initial draft. The descriptor is the teacher who provides feedback. The teacher learns from ground truth data. The student learns from the teacher's revision. Over time, the student improves and can better initialize the teacher's refinement, making both more effective. Formally speaking, the generator amortizes the descriptors MCMC and jumpstarts the descriptors MCMC. The descriptors MCMC refinement serves as temporal difference teaching of the generator. Cooperative learning offers several benefits. They combine the best of both energy-based models and latent variable models. Sampling is efficient. The generator jump-starts Markov chain, Monte Carlo sampling. Training is stable and avoids adversarial issues seen in adversarial learning. The model achieves higher sample diversity and realism compared to standalone generators. Generative cooperative networks can also be extended to conditional version for conditional learning. For example, by conditioning both the descriptor and the generator on input variables, we can perform tasks like conditional image generation and pattern completion. Generative cooperative networks have found applications in a wide range of domains. Image generation, such as texture, object, and scene generation. Video generation, such as dynamic video synthesis, pattern completion, like image inpainting, conditional image generation, and unsupervised image-to-image translation, such as image style transfer. Here are examples of generated images by cooperative learning for scenes, objects, and textures. Each case shows synthesized examples alongside observed one. The model captures both global structure and local detail quite effectively. Generative cooperative networks can also model temporal dynamics. Both descriptor and generator need to be equipped with spatial temporal neural networks to handle dynamics patterns. Descriptor requires a bottom-up spatiotemporal neural network to serve as its energy function, while the generator uses a top-down spatiotemporal neural network to perform the transformation. We show synthesized video samples, such as fire, waterfall, flashing lights, and vapor. The synthesized clips demonstrate that the model can learn coherent motion and appearance patterns over time. Another application of generative cooperative networks is image inpainting. Given a masked or corrupted image, the model can collaboratively complete the missing regions. Before performing the inpainting task, the model is trained on a fully observed data set. During inpainting, the generator first infers the latent variables by sampling from the posterior distribution, conditioned on the visible pixels using MCMC. Once the latent variables are inferred, they are mapped to the image space to produce an initial recovered image. This initial output is then passed to the descriptor, which further refines it through a few steps of Langevin dynamics, resulting in the final inpainted image. As you can see in the examples, the model effectively fills in missing regions, generating content that is both plausible and contextually consistent. The conditional version of generative cooperative networks can be applied to conditional generation tasks. Given an input, such as an edge map or a semantic segmentation map, the model can generate realistic outputs that are well aligned with the conditioning input. The model is trained on paired data consisting of input conditions and their corresponding target output images. This capability is particularly useful for applications such as image editing, guided content generation, and controlled image synthesis. The framework can be further extended to the unsupervised image-to-image translation problem, where the training data consists of two unpaired image collections from different domains. To establish a correspondence between these unpaired domains, the proposed framework learns a pair of cooperative networks with cycle consistency, enabling two-way translation between the domains. Each cooperative network includes an energy-based model and a latent variable model, modeling the distribution of one domain. In this application, the model learns to transfer style between different image domains For example, transforming real photos into paintings of various artistic styles, all without the need for paired supervision. To conclude, generative cooperative networks are a powerful class of models that unify energy-based models and latent variable models. The generator acts as an amortized sampler. The descriptor is trained by maximum likelihood using MCMC. Together, they enable high-quality synthesis, flexible conditioning, and robust learning. Applications span image and video generation, inpainting, conditional modeling, and style transfer. Thank you.